Hello. Today we'll be talking about inscribed angles and inscribed polygons. That means inscribed in a circle, such as this. This is an inscribed angle. Remember, we measure an arc according to the angle. It's subtends, but we measure this angle from the center. We draw a line out here and a line out here, and the angle measure is the same as the measure of the arc. Now if we start our angle way over here, well, that's not the same thing. The measure of the arc is not the measure of this angle here. We have to start at the center of the circle for that to be true. We're starting down here. Well, if you were to draw a line in here and out here, I think you could easily see that if C were the vertex of an angle ACB, it would be much wider than this one. As we move back, we can move even outside the circle if we want, this angle gets smaller and smaller. But that doesn't mean that it has to be exactly 1/2. That's the weird part. How do we know that's true? So we have ADB here and well, this is the center of the circle, so let's call it C. Well, what this theorem says is that ACB is double ADB. Why would that be true? Well, I think if we draw in some more triangles here, that's usually what we do with these circles. We're going to create triangles out of radii. That way we know that they're the same length. The radii are all the same length. And we'll see what that does for us. Well, we only needed to draw one more line. This is a radius, this is a radius, and this is a radius. Okay, so far. Now, since these are both congruent, this is an isosceles triangle here, this DCA. Oh, that means the base angles are congruent. Let's call them alpha. This is alpha, and this is alpha. Okay. And here, well, of course, this is a radius still, and this is a radius. So, again, we have another isosceles triangle. Now let's call this angle beta. And it's the same here. Now, I had to move C over a bit for what I'm going to do next. Always putting the labels in the wrong spot. What we have to do now is think back to our exterior angles theorem. Remember, if we had a triangle, well, it looks more like a pointed mountain, doesn't it? Well, anyway, pretend that's a triangle. We have angles here with, say, alpha, beta, and gamma. Well, remember our exterior angles theorem says that this exterior angle equals the sum of the two opposite angles. And that should be easy to remember because this is a straight line. So it's 180 degrees. So this angle plus this exterior, let's call it angle E for exterior. Maybe EXT, how's that? This exterior angle plus gamma equals 180. But these two plus gamma equal 180. So this exterior angle must be the same as these two. Actually, the sum of these two, pardon me. Well, why would that matter? Well, let's suppose I continue this line here in order to produce an exterior angle for this triangle. And it's getting a little crowded in here. Oops. This exterior angle might be more obvious if I just remove this part. How's that? Now you can see that we have an exterior angle right here. back, otherwise they might not match up if I get... well, this exterior angle is equal to the sum of these two opposite angles. What would that be? Well, alpha plus alpha is 2 alpha. And exactly the same thing is true over here. This right here is the exterior angle of this triangle, DCB. And it, of course, is equal to the sum of the two opposite angles, which are both b, so that's 2 beta. And of course we have an angle addition postulate, which says that this total angle is alpha plus beta. So, in the first place, we have that the measure of, we'll say, angle ADB that equals alpha plus beta. Well, what's this? ACB. Well, once again, we use the angle addition postulate and get that the measure of angle ACB equals 2 alpha plus 2 beta. Well, that's just 2 times alpha plus beta, right? But this is alpha plus beta. That's the measure of this angle here. So we just showed that the ACB is double ADB. All we had to do is complete the triangle here, use our theorems about isosceles triangles, and we've got it. At least that's true when the center is between the two rays. There are different cases here. These triangles that I just drew, they work as long as the center is inside the angle. What happens when it sits on one of the rays that produce the angle, or one of the segments that produce the angle? Now let's take a look. If the center lies on one of the segments producing the angle from which we derive the measure of this arc, here's the center right here, that means that one of the segments is a diameter. Well, we can do the same thing. We've got that the exterior angle here is equal to the sum of the two opposite angles. Well, that's 2 alpha, right? And what was ADC, or ADB, look at it either way, it was alpha. So once again, we have that the smaller angle is exactly 1/2 of the large one if it's measured from. And they frequently write arc also to indicate that it's the measure of this angle here, 2 alpha. And so you could write that the measure of arc AB equals 2 times the measure of angle AD, call it B, what the heck. Notice ADC and ADB, they're the same angle. You take the small one and double it and you get this one. That's when the center is actually on one of the lines producing the inscribed angle. The last case, what happens if the center is outside the inscribed angle? What can we do with that? Is this theorem still true? How would we show? Well, we know that if it goes through the center, this theorem holds. So why don't we just make ourselves a diameter here? Now let's say that DE is our diameter. Well, from the previous case, we know that ADE is 1/2 of ACE. That is the measure of the arc AE. But what is the measure of the arc AE? AE. Wow, that's... So we have the measure of arc AE. That's really a hard thing to say fast 10 times, isn't it? Is AB plus the measure of arc BE. Now, so what? What does that get us? Well, ADE, we know from a previous theorem, is half of the arc AE. So we have that the measure of angle ADE, that's the one we created by adding the diameter here. The measure of this is 1/2 of AE. We already know that from a previous demonstration. So that's half of the measure of arc AE. This large one is double this ADE here. But remember, we're really concerned with this one here. We need to show that ADB is half of AB. But we're getting there. We can easily see that this whole thing is double the small one. We just have to break them up. And when we use our angle addition postulates, we can throw out this part and end up showing that half of this small angle is equal to the measure of arc AB. And how do we do that? Well, again, from our angle addition postulate, we have that the measure of ADE is equal to the measure of ADB plus BDE. Well, we already showed that the measure of BDE is 1/2 of the measure of the arc BE. Well, that means that we can just cancel these. BDE equals this, so we just subtract from each side, and what are we left with? Well, this we have to cross out because this is no longer true. But this part, in other words, the equality doesn't hold anymore because we've subtracted these two. Just look at this part. And what do we have left? The measure of ADB equals 1/2 the measure of the arc AB. That's the last case of this. So in every single case, it works. Whether the C is inside the angle, C is on one of the segments or rays that produce the angle, or chords that produce the angle, or it's exterior to the angle. In every single case, this holds. By the way, an angle whose vertex is on a circle, that's called an inscribed angle. I don't remember if I mentioned that or not. I've been talking about it as if you knew what they were. And the arc created by an inscribed angle, that's called the intercepted arc. The arc that intercepts this. And it's, you kind of need to know that to work this problem. This is the intercepted arc here, AB. And they're saying that this angle is congruent to this angle. And that's really pretty easy. From our previous theorem, we have that ADB, that is the measure of, well, shoot. I went ahead and wrote it out. You could probably do this in your head. ADB is exactly half of the measure of the arc AB. We know that from the theorem we just proved. ACB, well, it intercepts exactly the same arc. So it's half of the measure of the arc of AB. In other words, we have two angles whose measure are equal to exactly the same thing. So that means that these two are equal. I wonder if that's... Can you draw a curved equal sign like that? Well, I just did, so I guess you can. But these two are congruent. Well, their measures are equal, which means that they must be congruent. So there's the squiggly line that goes on top of the two straight lines. So they have to be congruent. It's actually practically a corollary from the first theorem. Here's another theorem. This one, again, follows directly from our very first theorem, very easily. But I can see whether we call this a theorem, because this was probably something important to the Greeks. If you don't use a lot of variables, you can rely on measurement to make sure that you have a right triangle. Remember, we have our 3, 4, 5, so we could measure all the sides. And if they come out to 3, 4, 5, then we know we have a right triangle. Remember, Pythagoras' theorem goes both ways. L squared plus L squared equals C squared. On the other hand, if the sum of the two sides squared equals the other side squared, then you have a right triangle. You remember that from previous chapters. But there's another way to make sure you have a right triangle. And it's even easier because you don't need to do much measuring. A circle is always very easy to draw. A primitive person could draw a circle with nothing but a stick and a piece of string. You put a stick in the ground right here, extend your string out, hold it tight, and make a mark in the ground right where the end of the string is, and you'll automatically produce a circle. After that, finding a diameter isn't too tough because it's the largest chord. So if you had something like a stick, you could put it on one side and look at where the other side of the circle intercepts it. And it'll start, if you put the stick here, you'll notice that the intercept point goes to the right more and more and more, and then starts going off to the left again. The part where it's largest, where it gets larger and larger and then starts getting smaller, well, that would be the diameter. So again, you wouldn't have to take any measurements to find the diameter. And once you've got that, you got these 2 points, any point you draw on this circle and then connect them, you're going to end up with a right triangle. So that's one way. Another way to always make sure that you have a right triangle. And why would this be true? Well, heck, look at this. We got arc AC. Well, that's on a diameter. Diameter produces a semicircle, a half circle. What's the arc measure of a half circle? 180 degrees. Well, since the intercepted arc is 180 degrees, this angle here, ABC, which stems from the inscribed angle, must be half of that, which is 90 degrees. Boom. Very easy theorem. Follows directly from the first one. Well, this one looks a little weird, but it's not too bad, really. Oops. How in the heck are we going to prove that these opposite angles add up to 180? Well, once again, we're going to use arc measure. For instance, EDG. That's the measure of arc. That's 1/2 the measure of arc EG. In other words, let's take a look at the two opposite angles here, EDG. Well, that's half the measure of the arc EG. Okay, so far so good. What about this angle here, EFG? Well, that's half the measure of this arc, GDE. But if we take the arc from here to here, and then take this arc from here to here, what did we just do? We went all the way around the circle, didn't we? Which means that this arc plus this arc must be 360. And I should have put an M in here. It's not 1/2 the arc, it's 1/2 the measure of the arc. Well, the measure of these two add up to the sum of these two things here. And what are these two? Well, as I said, we take EG and then GDE. Well, that's all. I should have done that. That's all the way around the circle, which is 360. So this part right here is 360. That's the measure of those two arcs. I mean, the sum of the measure of those two arcs. But there's a 1/2 in front of that. So that's 180, and that is angle EDG. That's this one here, plus EFG, or angle D and angle F. You could call them that also. Well, quadrilateral. It's 360 degrees all the way around. These two add up to 180. That means there's 180 left over to be distributed across these two. We don't know what these are. We don't even know that they're congruent. All we know is that the opposite angles have to add up to 180 because of this stuff here. It's actually pretty simple. Again, we used our Inscribed Angle theorem, relating the measure of the arc and the measure of the inscribed angle. And once you do that, everything drops out pretty easy. Well, now that we've got all these theorems down, let's work some problems. Here's one that uses our Inscribed Angle arc measure theorem, one that says that the inscribed angle is half of the arc measure. So this arc right here, WY, this must be double this, which is 150. And this 110 here, I believe, is indicated, it was designed to tell us that the arc YX is 110 degrees. So we've got 110 and 150, that's 260. The whole circle has to add up to 360 degrees. So I guess this is 100 degrees. Pardon me, I think I just said 160, but I wrote 100. 100 is the right answer. Maybe I've got 60s on my mind, I don't know. Anyway, this is real simple. We just used our basic arc addition postulate, which says exactly what you'd expect it to say. It's 360 all the way around, and we've accounted for 260 of them, so that leaves 100 degrees for arc WX. Well, looks like our politicians are trying to do geometry again, and of course they messed it all up. What's wrong here? Well, let's see. We've got QR here. No problem. That's got to be 180, right? How do we know that? Because it goes through the center of the circle. See, it says circle C. We know that C is the center. QR is a chord which goes through the center, so it's a diameter. The measure of that arc is 180. The measure of this arc is 45. Well, pardon me. The measure of the inscribed angle is 45, which means the measure of this arc would have to be 90. Well, let's see here. 180 and 90. Kind of looks like 270 to me. Well, 270 plus 100 doesn't add up to 360, does it? So, what would be the problem here? Well, we could change this to 90. Everything would add up. Or suppose we left it at 100. Then this would have to be 80. If we change this to 80, and we can make this 40. And that would work also, I think. 180 is 260 plus 100 is 360. Yeah. So he or she inserted the measure of an inscribed angle in an arc, and they don't go together. One or the other could be right, but they couldn't both be right. That's two ways to correct the error. Here's a third way. Could have just called in sick and stayed home. That's usually when politicians do their best work. Well, they tell us that ADC is a central angle. I don't think I've mentioned those. Central angle just means that the vertex is the center of the circle. So we know that this is circle D now, because it's a central angle. With ADC being 60, we know that the arc has a measure of 60. Remember, the arc is measured according to the central angle that it subtends. However, we have an inscribed angle here which intercepts exactly the same arc, ABC, and they want to ask you, what would the measure of ABC be? Well, it would be half the measure of the arc, which is 30 degrees. There's no point in even looking at the other ones to see if they make sense. We just had a theorem and spent some time proving it, that this angle ABC is exactly half of the measure of the arc AC, or the measure of the angle ADC. They're pretty much the same thing in terms of measure. They're both 60 degrees, which means that the inscribed angle is 30 degrees. Now in this problem they'd like us to find the values of M and K. Well, this is pretty easy. We just had a theorem which said that an inscribed polygon, that's exactly what we have here, opposite angles, opposite vertices, the measure of those opposite angles add up to 180. So we have 2k plus 60 adds up to 180, and m plus 60 add up to 180. So what I have to do is write m plus 60 equals 180, or m equals 120. Very easy. And you do the same thing here, which would lead to, well, you get 60 on each side, so it would follow directly that 2k equals 120, or k equals 60. And they didn't ask, but that tells us we have an equilateral trapezoid, doesn't it? In fact, we already knew that from the fact that these two base angles were congruent, and that meant that these were going to end up being congruent also. But we still had to figure out what the heck they were. And there might have been other ways to do it, but this is the way to do it, which uses the theorems in this section. Here we have another one. It's just simple algebra. You just have to know which equation to set up. The measure of the arc, e.g., is 12x plus 40, whereas the inscribed angle, which intercepts this arc, is 8x plus 10. And we already know that the measure of this arc must be double the measure of the inscribed angle, or we could say the measure of the inscribed angle is 1/2 of this. Which one do we want to use? Well, let's say that 2 times this equals this. In other words, 2 times the interior, the inscribed angle, pardon me. That's 8x plus 10 should equal 12x plus 40. That's all you had to do. You set this up. Now we can solve pretty easily. For instance, we divide by 2 and get that 6x plus 20 over here. Let's subtract 10 from each side and get that 8x equals now as we finish up our algebra here, we get this, subtract the 6x and get 2x equals 10, or x equals 5. And is that, yeah, there it is right there. This was all you had to do in this problem, was recognize our inscribed angle theorem, that the inscribed angle is 1/2 of the arc that it intercepts. As soon as you say that, you're pretty much done. This is all just really easy algebra. Yeah, this problem looks kind of complicated, but it might not be too bad. They're telling us we have, well, they say C is a right angle, but of course they didn't need to tell us that, because we already know that a 3, 4, 5 triangle is always a right triangle and that this would have to be a right angle. No way around it. But they included this for people who aren't as smart as us. Now, if you draw the smallest possible circle through C, what would that mean? Well, that means, through C and tangent to AB. That's an important part. Which means it has to touch AB and go through C. The smallest possible circle that could do that, well, what's the smallest distance from a segment to a point, or a line to a point? It's the perpendicular distance. So, it's going to get kind of crowded if I do it here, I think. So I'm going to redraw another right triangle over here. And what we're going to have to do is figure out the perpendicular distance from this segment to the vertex here. However, that looks like an altitude to me, doesn't it? Hope it looks like an altitude to you, because that's exactly what it is. That's kind of the definition of the perpendicular distance from the vertex to the opposite segment. That is the altitude. And of course it is also the minimum distance. Look at it either way. Why does that matter? Well, look at this. When we connect J and K, those are the endpoints of this 90-degree inscribed angle. So that tells us this has to be 180 degrees. The measure of this arc is 180. Well, if the measure of this arc is 180, that means JK must be a diameter. And diameters are all the same. They asked us to draw the smallest possible circle. To do that, we minimize the diameter, the smallest circle that goes through C and just touches AB. Well, this altitude here is going to be our smallest possible diameter. On the other hand, JK is also a diameter. So if we figure out our smallest possible diameter, which is our altitude, we'll know what JK is. Now if I redraw the triangle over here and produce an altitude, remember what happens when we draw an altitude from the hypotenuse to the right angle? We automatically produce three similar right triangles. The original right triangle, plus the small one over here, and the big one over here. Let's call this H for, well, yeah, what the heck. H for height, not hypotenuse, height. Well, we have all the measurements for this triangle. So using the ratios from similar triangles should be pretty productive. We've only got one thing here that we don't know. And what is that? Well, for the small triangle, this is the longer leg and this is the hypotenuse. So let's write that H over 3. That's the ratio of the longer leg over the hypotenuse for this triangle is going to be the same as the longer leg, the hypotenuse, which is 5, over the longer leg. So we get and these work out much better if I don't get confused. We have H over 3, that's the longer leg over the hypotenuse for this triangle. Well, the longer leg here is 4, and the hypotenuse is 5. Well, that leads to H equals 12 over 5. However, H is just this diameter here. I can't say much about the way I draw the circle. In fact, I can't say much about the way I drew this altitude either. But this altitude probably should have used drawn the circle, just shifted over a little bit to the left so it would touch right here and not here. but analytically, the diameter of the smallest circle has to be the same as the distance, perpendicular distance, from AB to C, which is the same as the altitude. Well, any diameter is the same as any other diameter, so that is also the length of segment JK. You really just need it to spot, well, remember your little similar right triangle things by when you drop an altitude. In this case, we're not really sure. Drop it from the right angle vertex down to the hypotenuse, you automatically produce 3 similar right triangles. We could have used this one over here too. In fact, I think we did use this one, didn't we, now that I think about it? No, we used the big one and the small one. We could have used the big one and the second biggest one. You got 3 triangles to choose from. They're all similar, so whatever is easiest for you. In this case, I chose to use the ratios between the small triangle and the original large triangle. Now in this one, they'd like us to show why AB is tangent to circle C. Well, what's the easiest way to show that something is tangent? In fact, it's one of the only ways I can think of that we know about in this class. To show that it's perpendicular to a radius. In other words, we draw a line from the center to the point of possible tangency. If this turns out to be perpendicular, radius is perpendicular to this line touching, it seems to be touching the circle. Not every line perpendicular to a radius is a tangent, but if it seems to be touching the circle, we can make sure that it's tangent by checking to see if it's perpendicular. So how are we going to show that this radius from C, the center of circle C, out to the circumference of circle C? Well, luckily, the center here for circle C also lies on circle M, which means we have a line here which just touches, and they tell us that this is a diameter, or at least they tell us that M is the center of circle M, which means that this has to be a diameter because it passes through the center. If we produce a triangle here, we connect up AB, and then we connect up CB. Well, this triangle here is inscribed in circle M, and one side is the diameter, which means this is a right angle. So, well, that's what we needed to know, that this radius was perpendicular to this. So we're done. It really didn't take as long as extended response would seem to indicate. What makes it easy, really, is that the center of circle C lies on the circumference of circle M. If that weren't true, we'd be out of luck. Well, that's about it.